Hello, my name is Ivory Scherphorn. I am in the 575 portion of this class. I have done two pseudocodes, one from chapter 4 and one from chapter 6. I have two Word documents up. The one on the left will mostly be used for referencing my pseudocode as we go down through the other requirements in the homework assignment. And on the right, I will use, to reference uh, the pseudocode. So I'll be mostly using the right side, the right document. Anyway, so let's start. So I did 4.1-2 says write pseudocode for the brute force method of solving the maximum subarray problem. And your procedure should run in theta of n squared. So if we remember, the maximum subarray problem in the textbook used the example of buying and selling stock. So what would be the best 2 days in n amount of days? Not necessarily consecutive, just two best days of n amount of days to buy stock and sell it. Now, of course, that means if you buy stock, it has to be at least 1 day before you sell it because you can't sell before you buy. So I use my own example or my own array. I use the indexes as also the days. So the first index is 10 to 7 to 3 to 8 to 9 to 2. So I is representing the by date. This is my outer loop because I have an outer loop and an embedded loop. So my outer loop is the by date or the purchase day. Again, it always has to be at least one behind the sell day because again, you can't buy after you sell, doesn't work. And the result from this array, if I run my code, will be at index 2. So right here for value 3. And J is my sell day. The sell day, it has to be 1 day after the buy day. And again, it's embedded in the loop with index I or of index I. And if we were to run my program, it would return 4 or index 4, which would be the value 9. And the max profit that you could get from every iteration of the loop and embedded loop would be 6 because 3 and 9, the difference is 6, and it's the profit is greater than 0, so it's a positive profit. So the max you could get is 6. So let's go over here to the left and look at my code. So I have the brute force method or function. My first line is just creating the max prof, which is max profit. So I can compare it with the profit that will be distinguished within the embedded array, embedded loop, sorry, of J. Then we have array n, and I equals 0 just for initiation purposes. So for I up to length minus 2, which is the outer for loop, it goes to length minus 2 because it has to be 1 day before the sell date. So I can't have it end on the last part or the last day because then there's no time to sell. So it'll be 2 days before the second to last day. And then for the embedded for loop, will be J. J equals I plus 1. Again, this just keeps it. So J is always at least 1 in front of I. So you can keep comparing. And then J up to array length minus 1. So it's the last day that you could sell, the last day or the last section of the array. And in this embedded loop, I have a while loop. So as long as array at index J is greater than array at index I, then the profit will be array at index J minus array at index I. And this is just to make sure that if you subtract array at index j minus array at index I, it will be greater than 0. Because we don't want a negative. A negative is not a profit, it's a loss. So we're just trying to keep track of only the profits and what are the largest of them. And so if profit, or sorry, yes, if prof, the comparison prof in the embedded loop is larger than max prof, the max profit that we can get, then the new max prof will be the value of profit. And as the loop iterates, it's just going to keep updating until finally the outer loop and the outer loop and the inner loop end. And at the end of it, it'll return I, which is supposed to be the purchase day, J, the sell day, and the max profit that was obtained from this search. So let's come over back to the right document and do the time complexity. So I skipped 1 through 3 here, because they're all assignments, they're all constants. So I just went straight to line 4. So line 4 is this for loop, this outer for loop, and it goes to n minus 2. So it takes array length, which is n, and it goes to the second to last, so it's minus 2. And it runs n times, last, change this to last element. And then, so it goes from second to last element. And then line 5 is the embedded for loop. The embedded for loop here goes to the length of n, which is the array length, minus 1. So it's at the end. But since it's embedded, you have to multiply it by n minus 2, which is the outer for loop. So that'll be, n squared minus 3n plus 2. But we'll get to that down here in the time complexity equation. But lines 6 through 10 are all constants. So the while loop here is a constant because we're just comparing. The line 7 is just arithmetic. It's just basic arithmetic and assignment. 8 is just comparison. 9 is just assignment, and 10 is just returning. So these are all constants. So really we're only focusing on the outer loop and the inner loop. So again, if we do the time complexity, it's O n minus 2 outer loop plus, theta n2 outer loop plus theta of n squared, let's say n2, theta n minus 2 plus theta n squared minus 3n plus 2, and then all of the constants. But we have to drop the constants and take order of growth, which is the order of growth, is the highest exponent. I'll say the highest exponent in this case. So it'll become t of n equals theta of n squared, because we will drop the constants in here as well. Plus 2 is a constant. Minus 3n is a constant. Minus 2 is a constant. So really that would leave us, theta of n plus theta of n squared. But again, we're taking the order of growth. An order of growth would mean that theta of n squared is the highest. So that is our time complexity. And to show that with the summation, I did the summation of I starting at 0 to n minus 2 is the outer loop. And then j equals, or multiplied by the summation of j equals I plus 1 to n minus 1 with a constant of 1. And if we do the math, if we do n minus m plus 1, it'll become summation of I equals 0 to n minus 2 multiplied by n minus I minus 1. Now, if we keep doing the summation until this I equals n minus 2, it'll become 1. And then so if I equals 1, we follow this equation, and or I equals 1, 2, n minus 1, the summation of it, we will get this equation here that we learned about, that is n multiplied by n minus 1 divided by 2. And if we do the math real quick, it's n squared minus n over 2, so then becomes theta of n squared for this formula of this function, which is what was asked for in the beginning. So this is this follows it. The space complexity is array of n elements, because n elements is present, so it'll be n. Max prof is just a variable, so it's just 1. Profit will be n squared. It's not exactly n squared, because it only goes to n minus 1, it has to be multiplied by n minus 2. But just for simplicity purposes, if it's embedded inside, or if it's inside embedded loop, it has to be n times, and then the outer loop, it multiplies again by n, so it's n squared. Because the rest, like we did earlier, are just going to be constant, so we're just going to say it's n squared. And I'm going to use big O notation because this is the worst case scenario. The worst case scenario is that it has to update every single time. So I'm going to use big O. And then the return is just 1 unit. So the result is n squared plus n plus 2. And of course, we drop the constant, so it's a big O of n squared is the space complexity of this. So the loop invariant that I decided was, identifies max profit using max profit variable. So at initialization, before the loop begins, prof equals 0, because they're right over here on the left side, because there is no profit. It hasn't started yet, so you can't make a profit. And the maintenance, is the outer loop I at array I, array at index I, makes a comparison with array at index j, the inner loop, to compare profit and max profit. And by doing so, right here, we do array at index j minus array at index I to equal profit. And if, again, if profit is larger than max prof, then the new max prof is the value of profit, or of prof. And this loop will just continue like this until termination. So at the end of the loop, at the end of each iteration, it's still showing what the max profit is so far that that has been found so far. So at termination, the last value of prof that was assigned to max profit here will be returned after the comparison from the two loops, or using the two loops. And termination will occur when I is at array length minus 2 and when j is at array length minus 1. So that is for chapter 4 for the brute force. Now let's go to chapter 6. Let me scroll over here as well, so you can see my pseudocode. Here we are. Okay, so back to the brain. So I did 6.2-2, starting with the procedure max heapify, write pseudocode for the procedure min heapify that takes array and an index of I, which performs the corresponding manipulation on a min heap. And how does the running time of min heapify compare to max heapify? So as we know, max heapify is a heap that every parent of its children has to be larger. So obviously min heapify is the opposite. Every parent, this is a parent, or in this case this is the root as well, but a parent is supposed to be smaller than all of its children. But as you can see in this example I created, it's not. That's not true. So 6 is definitely larger than 2, so this is incorrect. But here's my array: 6, 2, 7, 8, 5, 10, and 12, and corresponding array. I put these 1, 2, 3, through 7 as the heap positions. And we're going to see through my pseudocode how we're going to correct this, how we're going to rectify this. So first, let's start with the left child. The left child is just the left of I. So I is the parent or the root. It's what we're comparing with. We're starting with the parent and or the root. So we gotta find the left child of that. So left child is just left of I, right child is just right of I. And I create a variable smallest so I can compare without moving too much, just compare once really at the end. So we'll do if I, the parent and or root, is greater than left child, and left child is within the heap size, then the smallest is now the left child. Because remember, if it's a min heap, we want the parent to be the smallest. But if that's not the case, then the new smallest has to be the left child. And of course, if this is untrue, else the smallest is the parent indeed. Good. Now we have a smallest. It's either left child or I. So if smallest is greater than right child, because we want the right child or the smallest to be, be present, then the smallest will now be the right child. So right child will be assigned to smallest. Now this is where we compare smallest with I. This is the final. So if smallest is not equal to I, smallest is not I, our original, our parent and our root, then we have to swap I and smallest in our array, in our heap. And then we will use this new smallest and recursion call this again from array I, and the smallest will become this I, and this will start all over again. So by the end of it, this should be our result. 2 should be the root slash parent, the root of the min heap, and then 5, 7, 8, 6, 10, and 12. So, sorry, so the time complexity mostly are constants. I think all of them are constants until we get to the recursion call. But so left child constant, right child constant, we're just assigning variables. Smallest constant, creating variables, assigning variables. If 4 is just a comparison, line 5 is just assignment, 6 is a comparison, line 7 is assignment. So comparison, assignment, comparison, assignment, until we get to line 12. Now, because we are calling this again, and this is on a binary tree setup, because what heaps are created from are the binary trees, you have to go down the tree. So if the tree at the root is n, then the 2 left and right children are n or divided by 2. And the children of those children are n divided by 4. And the children of those children are n divided by 8. So we have to take the log of n in order to figure out when the tree will end. When are the last leaves? So let's say, well, let me show the example, because I did do a reference of opengenius.org, and I liked their visual example of this better than the textbook. So I also like to do things literally with numbers and figure it out from there. It's easier for me personally. So you take the first iteration, the children of n, and divide by 2. The second iteration, and divide by 4. Third iteration, and divide by 8, until you get the log of n. This is that iteration of log of n, which would be n divided by 2 to the log of n. So for example, say that n is 16. The first one would be 16 divided by 2. The second one would be 16 divided by 4. The third one would be 16 divided by 8. And the fourth one, because log of 16 base 2 is 4, so the fourth one would be 16 divided by 16, or 16 divided by 2 to the log of 16, which would be 2 to the 4th. See, they're corresponding. And 16 divided by 16 is 1. So that's the end of the tree. So that's why I believe that this would take, for the recursion call, it would take log of n times. So of course we have all the constants. So theta of 1 plus, theta log of n like I described earlier. So the result, if you drop the constant, would be theta of log n. That's how, that's the time complexity, the time complexity of this algorithm, I believe. So the space complexity is just a constant because I'm mostly just assigning and creating variables. And even just calling this min heapify, I'm just calling a function. So I believe that's a constant. So I believe that it is just theta of 1 for space complexity or a constant time. Now for the correctness, it's a little difficult because there is no loop. So I don't believe I can do loop invariant, but I can try to explain this again a little bit better. So basically this algorithm will always compare the parent to its two children, find the smallest of the three, and switch if the parent is not the smallest, because it's a min heap. The parent needs to be the smallest of the three in its heap size in the heap. So let's start with 6. Let's say I is at 6, so index 1, but we'll say it's 6. So the left child of I index 1, 6, is 2, and the right child is 7. Right now we don't have a smallest yet, so we're just finding the smallest. And once we find the smallest, that'll be the end of the determination. So anyway, so if I, 6, is greater than 2, which it is, and 2 is within the heap size, then the smallest here, the smallest is now left child. So right now smallest is 2. We can skip this else because we have decided that the smallest has been assigned to the value 2. So if smallest, this 2, is larger than the right child, the 7, then the new smallest would be the right child, but that's not the case. 2 is very much smaller than 7. So the smallest stays 2, or yes, the smallest keeps the value 2 at index 2. So now, because smallest does not equal I, remember I was 6, and smallest is 2, so smallest does not equal I, does not equal 6, they will swap. So this 2 will become the new root / parent, and the 6 will become the new child of 2. And that makes sense because we're doing a min heap. So again, the parent, or in this case also the root, has to be the smallest number in the heap size. So, or in the heap in general, but in the heap size. So now the smallest, which will be 6 here in place of 2, will be put back in once the recursion call is called, and will become this new I. So I is still 6 in this case, but now because it's here where the 2 was, it will compare with left child 8 and right child 5. Now just real quick, we know that 6 is smaller than 8, so the smallest in this case is I. But 6, this is 6, remember, because it's swapped. 6 is greater than 5. So now the new smallest is 5. And because the smallest does not equal I, the original, the parent, they have to swap. So now the 5 will come here, and the 6 will come here. And that will be the end of this algorithm because we have reached the end, we have reached the leaves of the binary tree. So it will, here it is. It will become this. So the first will be 2, because it's a min heap. It should be the smallest one up top, especially if it's a parent, but especially as a root as well. 5, 7, 8, 6, 10, and 12. And this will work every time depending, it doesn't matter actually, depending on the I, what you decide index I is, because you could do index I is index 3, or which is 7. So you could start at 7 and do the same comparison. Is 7 greater than 10? No, it's not. It's smaller, so it's fine. Is 7 greater than 12? It's not. It's smaller, so it's fine. So the smallest stays 7, and it will not have to move because this is the smallest. And we can do the same thing with 2 again if we wanted to. Now we compare 5 and 7. And if there was children, if 8 had children and 6 and 10 and 12 all had children, then you could do the same comparison there. Just use I for the index that the parent is at. So if I want to use 8, I just put in index 4, and it will do the same comparisons as if 8 had a left child and a right child. So that concludes my presentation. I hope it was understood clearly, and I hope that you were able to learn something new. Feel free to email me or contact me if you have any questions, and I hope you have a great day.